Bismillahirrahmanirrahim. Assalamu alaikum ji. So far in this course, we have been studying different algorithms for regression and classification, which are part of unsupervised learning algorithms. Because the data we had for these problems was a label data. For every input, we had the information about the desired output and during the training stage. And we could use this information to learn the parameters of the model for both regression and classification. We could use the labels to learn the parameters to train the model during the training stage. Today, we will start with unsupervised learning, which we use for the case when the data is not labeled. The question is, if the data is not labeled, what are we trying to learn? We want to discover the patterns in the data using unsupervised learning. We want to find out the hidden structures in the data. We want to find out the clusters in the data. Clusters mean a group of similar objects in the data. So that is the objective of unsupervised learning. So it is a machine learning technique in which we do not need to supervise the model. Instead, we allow the model to work on its own to discover patterns and extract meaningful information from the data. So let's talk about the outline which we will be following for this topic. We will start with introduction to unsupervised learning. In fact, unsupervised learning is also referred to as clustering. Although clustering is one technique for unsupervised learning, but we use these two terms interchangeably in the literature. So clustering, also known as unsupervised learning and vice versa. So after introduction to unsupervised learning and clustering, we will give you an overview of clustering, that what is clustering, how do we evaluate clustering, what are different aspects of clustering, and then we will talk about two techniques of clustering, partial clustering, in which we will focus on very famous, very simple algorithm, k-means clustering. And in hierarchical clustering, we will talk about agglomerative clustering. Right? Okay, let's start with introduction to unsupervised learning. So what is unsupervised learning? This is very similar to how a kid learns on its own. When we were kids, we used to intuitively lump groups of things we see into classes. Our goal of unsupervised learning is to have the same capability. In fact, also animals learn by a form of unsupervised learning in their formative years. So the main product of unsupervised learning method is some kind of structuring of the data that has not been fed in, or that's not part of the data. Data is not labeled. Okay, formally, the learning algorithm would receive unlabeled raw data to train a model and to find patterns in the data. And the machine learning model would gives us structured data, labeled data, or the data that was unlabeled in the form of clusters. It clusters the unlabeled data. So clustering, also known as I said earlier, unsupervised learning, and there's a historical connection. That's why we refer to clustering as unsupervised learning and vice versa. So is the most widely used technique for unsupervised learning, right? And therefore we'll focus on clustering. So in this course, okay, what is clustering? Clustering is we have the data which is unlabeled. Right. So we have these data points in some feature space, and objective is we want to group these data points. We want to cluster these data points. So a cluster is a collection of data items which are similar between them and dissimilar to data items in other clusters. So there's a notion of similarity. And we will see shortly how do we define this notion of similarity. So clustering is finding these blobs in your data, because inside these blobs, we're saying the data points in these blobs are similar to each other and they're dissimilar to the data points in other clusters. Right? So given the data group, similar points in the group, they form cluster. Okay? So we want to group similar points into the form of clusters. So that is the objective of clustering. What's the idea? So the idea is we want to group data into similarity groups, and we will refer to these similarity groups as clusters. And cluster, as I said, has a long history. In some fields, it is referred as classification. For example, statisticians, they refer to clustering as classification. Psychologists, they refer to clustering as sorting. People in marketing, the clustering is segmentation. So people give different names in different fields to this clustering. So formally, clustering means organize the unlabeled data into classes such that intra-cluster similarity is minimized, or it means the data points inside one cluster, they have low similarity, and inter-cluster similarity is maximized. It means we have a high similarity between data points of each class, right? So inter-cluster similarity is minimized, the similarity between clusters is minimized, and the similarity between data points inside the cluster, inter-cluster similarity, is maximized. Okay. This is in contrast to classification. We learn the number of classes and class labels directly from the data. In classification, we had the information about the classes, we had the class labels. But here, we want to learn the number of classes, the number of clusters from the data, and also some class labels. We assign class labels to each of these clusters, right? Okay, before we study different aspects of clustering, maybe very quickly we can talk about some of the applications of clustering. As I said earlier, it has been used in marketing. So in fact, clustering is used in almost every field. For example, medicine, botany, psychology, or it could be marketing, finance, economics, and so on and so forth. Yep. It's a long list. For example, in marketing, we use clustering for segmentation of customers and segmentation of markets so that marketing companies can carry out targeted marketing. Okay. So clustering could include clustering with respect to spatiotemporal demographic distribution of sales of products, right? That in this region or in this time interval, the sale, what's the distribution of the sale of some product, so that they can focus on this cluster that in this time interval, the sale is lowest in this region. So there is a need to carry out targeted marketing in this region. Another example could be insurance companies cluster policyholders to identify groups of policyholders with a high claim costs on average, so that they can focus on those policyholders, right? Clustering is used in text analysis. So grouping of a collection of text documents with respect to similarity in the content. So we have, for example, when you search for news in Google, so you get a grouping of news items when you search for an item, right? So you get a cluster of sports news, you get a cluster of politics news, and there's a cluster of the news or the items that are related to health, and so on and so forth. Right? So clustering is used in text analysis. We use clustering for anomaly detection. For example, you are getting a data from the sensors of the machine, and machine would be operating at some predefined operating points. And for those predefined operating points, sensors would be attaining the value in some region. Or you can say, if you're looking at the values of sensors in a multi-dimensional real space, the values of sensors would form a group when the machine is one state. When the machine is moved to other state, the cluster move to another position in the higher dimensional space. Right? So machine is moving from state to state, and these census values moving from blob to blob. If we can find, if so, during training, we have learned that these are clusters in which we get the data when the machine is operating under normal conditions, right? And we can use this information to find out whether there is anomaly. If we get the operating point that is not part of these clusters, so that can be classified, that can be characterized as an outlier, and we could detect anomaly, right? So clustering is also used in finance. For example, for the allocation of diversified portfolios of stocks, we can use clustering. Or in seismology, in earthquake studies, so we can clustering of epicenters of earthquakes are distributed around or along fault lines. We know that there are fault lines along where we have the continental boundaries, and along those continental boundaries we have epicenters. And when we cluster the data of all the earthquakes, we find that these epicenters are grouped along the fault lines, or using these epicenters, we can identify the fault lines, right? I could also mention more applications, but I think I gave you an idea that clustering is, in fact, the most utilized data mining techniques used to carry out segmentation, to carry out clustering, and for grouping of the data, and so on and so forth. Right? Okay, some of the aspects of clustering. So given the data, what do we need to carry out clustering? Three things. So we need to define a measure to quantify or determine similarity, because we want to group similar data points. We want to group similar objects from a cluster. So we need to define the notion of similarity, and we need to define a measure to quantify this similarity. Right? We need to define a criterion to evaluate the performance of clustering, to evaluate the quality of clustering. Some simple criterion could be we should have low inter-class similarity, and we have high intra-class similarity. This could be one way to measure the performance of clustering. We can also use ability of clustering to identify hidden patterns in the data. So this can also be used as a measure to evaluate the quality of clustering. So we need to define a measure for quantifying similarity. We need to define a criterion to evaluate the quality of clustering. And finally, we need algorithm. We need clustering techniques for grouping similar data points. Right? And there are different, these techniques are broadly categorized into different categories. And this includes partition clustering, hierarchical clustering, model-based clustering, and density-based clustering. Right? I will shortly explain each of these clustering types. Right? But in this course, we will focus on partition clustering and hierarchical clustering. Okay, let's look at these aspects one by one. The first, defining a measure to quantify similarity or dissimilarity. We can use distance metric to quantify dissimilarity between objects. Right? So mathematically, we quantify dissimilarity between the 2 points x and x dash using a real number given by a distance function, distance x dash. And we have studied this distance function in detail when we talked about the first algorithm, k nearest neighbors. We require this distance function to satisfy following properties. So it has to be non-negative. So it has to be symmetric. So obviously, if we cannot say that A is similar to B and B is not similar to B, B is not similar to A. So distance has to be symmetric. distance is 0 implies the two objects are same or they are exactly same. Right? They are same or they are exactly they're equal or they're exactly same. It's one and same thing, by the way. This is called self similarity. Right? The distance of x dash is equal to 0 implies x is equal to x dash. And finally, distance should satisfy triangular inequality. And so if so, these are the four attributes and four characteristics we require distance function to satisfy. And we studied earlier different definitions of distances. Minkowski distance and the special form of Minkowski distance is Euclidean distance, Manhattan distance, and Chebyshev distance. Euclidean is norm 2, Manhattan is norm 1, and Chebyshev is infinite norm. So we also studied cosine distance. I have indicated this in this red because this cosine distance just does not satisfy this triangular inequality. Nevertheless, we use cosine distance very frequently to measure the similarity to measure the angle between two data points, right? And we know that for categorical variables we use Hamming distance, right? So we've talked about a metric which we can use to quantify similarity or dissimilarity between the two data points, two objects. Let's talk about evaluation of clustering. How do we evaluate clustering? Unlike supervised learning, the evaluation of quality of clustering is a hard problem and is mostly subjective, as we don't have information about the true labels. We don't have information about the clusters. In supervised learning, we could define a loss function, right? Predicted value minus the true value, this difference is error. But here, we cannot define a loss function because we don't have information about the true labels or the correct clusters. There are different criteria which we can adopt to evaluate performance of clustering. So they're broadly categorized in two categories: evaluation using internal data and evaluation using external data. In evaluation using internal data, we use the unlabeled data we have for evaluation of the clustering algorithm. And whereas in using external data, we evaluate the performance of the clustering algorithm using some label data. So we run the clustering algorithm on the label data, assuming it would perform in the same way on unlabeled data. That is evaluation using external data. Okay, let me explain in more detail each of these. So evaluation of clustering using internal data. One measure could be intercluster separability, right? So we can measure of the isolation of the cluster. We can this could be measured, for example, using the distance function between the distance between the centroids of the cluster, between the centers of the cluster. For example, if you have these clusters, right? And we will define centroid shortly, but center means the average of all of the data points inside one cluster, right? Say for these clusters, so these are centroids, and we can define the distance between these centroids as a measure to evaluate the performance of clustering. So these distances would quantify intercluster separability. Alternatively, if we just focus on one cluster at one point in time, we can define intra-cluster cohesion, whether the points inside the cluster are concentrated or whether they are sparse inside the cluster. And that can be quantified by intra-cluster cohesion. So it is a measure of the compactness of the cluster, right? How compact is the cluster, how the data points are concentrated inside the cluster. A measure which is very frequently used for intra-cluster cohesion is the sum of squared error that quantifies the spread of the points around the centroid. So you take error between the centroid in every data point, and we square this error and we sum for all the points inside the cluster. So this would be quantifying the spread of the points around the mean, around centroid. Centroid is the mean, and we are measuring the difference from the center, and you square it and you sum. This is a measure of spread around the mean. And this can quantify the compactness of the cluster. Right? Okay, so these are the two measures which we use to evaluate the performance of clustering using internal data. Because here we're using the data we have used for forming these clusters. Alternatively, we can evaluate performance of clustering using external data. So the idea is we use label data to carry out clustering, and we measure the extent to which the external class labels match the cluster labels. So evaluation of clustering performance using the label data gives us some confidence about the performance of the algorithm on the unlabeled data. So this evaluation method is referred to as evaluation based on external data, because we're using external data, label data, to evaluate the performance of the clustering algorithm. If we assume each class as a cluster, we use classification evaluation matrix after clustering, right? Because we have the label data. Once we carry out classification, we reassign labels, and we have these clusters. And now we can use confusion matrix. We can use precision, recall, F1 score, ROC curve to evaluate the performance of the clustering. We can also use these two measures, purity and entropy, using for this evaluation using external data. So we did not define these two measures because these were used for evaluation of clustering. Let me define these two measures, purity and entropy. So we assume we have M classes and we have a data D with label associated with each data point is either 1 due to M. Okay. So we have a data set D, and in the data set D we have M classes. We use clustering algorithm to form the clusters of the data points. And let's say when you apply clustering method divides data D into M disjoint subsets. So D1, D2, D3, D4, Dm. Right? So if these disjoint subsets, so these clusters are the same, follow the same grouping we had with respect to classes, we say our clustering algorithm could separate data points for different classes very nicely. But to quantify this, we define two measures, entropy and purity. Let's talk about entropy first. So entropy is a measure of the proportion of different classes in each cluster. How do we define entropy? So for each cluster Di, we define entropy of a cluster Di as Rij times log of Rij. Let me define what is Rij. So Rij for a cluster I denotes the number of points of cluster J, of class J in cluster I. So this is kind of evaluating mixing, right? That's number of points that had the label of class J, but now they are falling in cluster I. Right? This is the ratio. So, and divide by number of points of class J. So this is a ratio. This is the proportion of elements, data points that had the label of class J, but now they are in the cluster I. And that's how we measure entropy for each cluster. And once we have entropy for each cluster, we take a weighted average of the entropy for each cluster, because each cluster could have a different size. So di as the size of the cluster. So entropy for di is scaled by, is given the weight that is proportional to the size of the cluster. And that's how we get the entropy of the dataset D. And this entropy is a measure of the proportion of different classes in each cluster. Right? Alternatively, we can use purity, which is very similar to entropy, but instead it takes into account the maximum mismatch between a maximum impurity in each cluster. So for each cluster DI, we define the purity as measured number of points of class J in cluster I, so same Rij, right? And we define the purity for the cluster DI that we take a maximum value over J. Right? So in cluster DI, we could have points of class 1, we can have points of class 2, we can have points of class 3. We take maximum number of mixing from the different class. In fact, it's a ratio for the different class. So that gives us a measure of purity, that how pure your cluster is. Right? If in fact it's a measure of impurity. If this is close to 0, I would say. So yeah, so it quantifies the purity of the cluster DI, right? And the total purity would be given by simply the same formula. You take a weighted average of purity for each cluster, and you get the purity for the whole data set D. So this purity, entropy, F1 score, confidence matrix. So recall, we are using external data to evaluate the performance of the clustering algorithm. And we should note here that we do not have labels associated with the data for the clustering problem. So evaluation on the label data does not guarantee a good performance on the data in which we don't have the labels. So this simply gives us confidence that we expect a clustering algorithm to perform well on the unlabeled data. Right? Okay, third aspect of the clustering algorithms. So in clustering algorithms, we usually optimize the following for a given number of clusters. So we either optimize tightness of the cluster, compactness of the cluster, cohesion of clusters. So these are the metrics for each cluster, right? Or when we talk about intercluster, we maximize separability of clusters, we maximize distance between the clusters. Right? So these are the metrics which we can optimize while finding out the clusters of the data. Ideally, we require clustering algorithms to be obviously scalable in terms of both time and space. They should be computationally efficient, and they should be able to deal with different data types, and obviously they should be insensitive to presence of noise or outliers. And they should be insensitive to order of input records. It simply means if they have some concentration of data points in some cluster, they should be insensitive to this asymmetric sizes of the classes or different shapes in the clusters. Algorithms should be interpretable and usable. It means we can, once we have these clusters, we should be able to infer some information. We should be able to relate the information conveyed by these clusters or these groupings of the data. Right. So broadly, as I said earlier, we have 4 types of clustering algorithms. Partitional clusterings, so divides data points into non-overlapping subsets such that each data point is in exactly one subset. And we will study in the next video this k-means clustering algorithm, one of the very famous, popular, very simple, computationally efficient k-means clustering algorithm in the next video. So this is an illustration that we are partitioning the data such that we don't have any overlap between the clusters. Another type is hierarchical clustering. It constructs a set of nested clusters by carrying out hierarchical decomposition, hierarchical division of the data set. And there are 2 types, agglomerative clustering and divisive clustering. We will focus on this agglomerative clustering in this course. So if you know agglomerative clustering, you can easily understand the concept of divisive clustering. Right. So in hierarchical clustering, if you have these data points, we obtain a set of nested clusters, right? So a cluster of 1 point, a cluster of, you have 2 clusters, cluster of these 3 points, and this could be a cluster of 1 point. Right? Or you can further divide this green cluster into 2 clusters. Right? So we have a set of nested clusters. We will see in detail how do we obtain this set of nested clusters, how do we carry out hierarchical decomposition of the data set. Another type of algorithm is model-based clustering algorithms, in which we assume that data was generated by a model and we try to fit the data to the model that defines cluster of the data. And then we have algorithms, density-based clustering algorithms, in which we assume the data cluster in the space is a region of high point density separated from other clusters by regions of low point density. So we assume that there are holes in the space, and the cluster in the space is a high point density, and there's a cluster in the space, another high point density, and we have a hole, we have a space in between these clusters. Right. So these are the broad categories of different clustering algorithms. We will talk about partition clustering and hierarchical clustering in the subsequent videos. We stop here and we'll continue in the next video, inshallah. Allah Hafiz.